Okay, so we're going to talk about a class of numerical methods called multi-step methods. And in particular, we're going to study an example of this, which is called the Adams method. So you might ask, well, what's the basic idea behind of this? Essentially what happens is that if you want to get a method which is extremely accurate, you need to be able to construct a very high order approximation of the solution. Okay, and that typically entails requiring you to evaluate the vector field at a bunch of points. The motivation, if you will, behind multi-step methods is that if you've evaluated the vector field at a bunch of previous times, is it possible to use those previous function evaluations to construct a higher order approximation of the solution? Okay, so let's look at what happens. So imagine this is the time interval t, okay, and you have okay, so you have tn, tn plus 1, all the way up to tn plus I would say tn plus s, if you will. Okay, and we're going to call s the number of stages. I'm sorry, the number of steps in the method. Okay, and the goal, if you will, behind a multi-step method is that given y at n all the way up to y at n plus s minus 1, right, you want to find an approximation y at n plus s. Okay, one thing, of course, you can do is you can appeal to the fundamental theorem of calculus as before. Okay, so you can write y at t n plus s as being equal to y at t n plus s minus 1, okay, plus the integral from t n plus s minus 1 to t n plus s of f evaluated on the vector field, okay, y of tau d tau. But where the art comes in, if you will, okay, is that so you happen to know what the y values at a bunch of previous times are, yn plus 1 all the way up to yn plus s minus 1. Okay, and you would like to then approximate this integral. But what you can imagine doing is that you know the function values, it's like at all these previous times. And so you have to evaluate this integral, but nothing prevents you from constructing the approximation to f by using all the data which is available to you, okay, at the previous times. So the idea behind it's like constructing the Adams method is that you approximate this integrand f y tau tau, right, by an interpolating polynomial which is constructed using the values of y's which you have yn all the way up to yn plus s minus 1. Okay, and in fact it's even possible to formally construct that interpolating polynomial using the as yet unknown solution at the new time, which is yn plus s. If you would construct it using only the data which you already have available to you, you can check that you will get a explicit method. So the ones which depend on yn to yn plus s minus 1 will give you an explicit method. And this is going to be what is called the Adams-Bashford methods. Okay. And if you actually use something which involves yn to yn plus s, right, where s and the n plus s term is the as yet unknown solution, then you get an implicit method which is called the Adams-Moulton methods. Okay. And you might ask, well, what is the benefit, if you will, to these implicit methods? So sometimes it's like you have better stability properties, but the other thing it's like which you get is that by including this additional point, you get one higher order of accuracy as well. Okay, so let's see how you can take this basic idea for a numerical method and then realize it in practice. Okay, so again, as a reminder, you want to apply the fundamental theorem of calculus, right? Y at Tn plus s equals to y at Tn plus s minus 1, right? Plus the integral from Tn plus s minus 1 to Tn plus s, right? F y tau tau d tau. Okay, and you want to construct an approximation of the integrand using the function values which are given to you. So previously we talked about constructing numerical quadrature rules, and if you recall, the basic idea behind constructing a numerical quadrature rule, the simplest idea, is to replace the integrand with an interpolating polynomial using, for example, the Lagrange form of the interpolating polynomial, and then exactly integrating that interpolating polynomial, and then interpreting that result as a weighted linear combination of the function values at the quadrature points. Okay. So what you do is you construct an interpolating polynomial okay. So let's call that P of t. Okay. So it's this sum from m equals 0 to s minus 1. So I'm going to first look at the case for the Adams-Bashford case where I only use the data which is already known to me and I'm not using the values at the new point. Okay, and so this involves evaluating the vector field at the solutions which you already know, yn plus m, Tn plus m, and then you multiply this into one of these Lagrange polynomials. Let's call that Lm of t. Okay, so Lm of t is a Lagrange polynomial. And the Lagrange polynomials are defined, it's like in terms of this Kronecker delta property, Lm evaluated at T n plus k, if you will, right, have the property that it is the Kronecker delta between m and k. So this means that it's 1 if m is equal to k, and then 0 if m is not equal to k. Okay, and it's easy to convince yourself that the way you get one of these So you know the zeros, it's like the zeros tell you where the roots are. You take the monomials, it's like with those roots, and you multiply them all together. And then you use this normalization condition to figure out what the constants are. So it's easy to convince yourself that what you get is the following. So L goes from 0 to s minus 1, which is sort of the case you have here. And then L not equal to m. Okay. And then you have t minus t n plus L over t n plus m minus t n plus L. Okay. So that's the Lagrange polynomial which satisfies this kind of Kronecker delta property. Okay. And the claim is that when you take that and you evaluate it at the times Tn plus k, then you'll recover the sort of interpolation data which you have there. Okay, so in any case, so what you have then is that you can use this in the following way. You can say that y at n plus s is equal to y at n plus s minus 1. So this is now the sequence of approximations, right? Plus the integral from Tn plus s minus 1 to Tn plus s, right? And then you replace the integrand f by this interpolating polynomial p of t. So this is sum from m equals to 0 to s minus 1 of f at y n plus m, and then t n plus m, and then you have to multiply it by this Lagrange polynomial. Okay, and you have to integrate this respect to t, basically. Okay. All right. So apologize. Okay. So what happens then is, again, you swap the order of the integral and the sum. So this becomes yn plus s minus 1 sum from m equals to 0 to s minus 1, right? And then you have the value of the vector field at the times multiplied by a coefficient, which is the integral from Tn plus s minus 1 to Tn plus s Lm of t dt. All right, so this is going to be some sort of weight, if you will. And then it's quite customary to have that the this time steps be equally spaced with an interval h here, and then by appropriately rescaling everything, what you can end up writing this as is you can write it as y n plus s minus 1 plus now a factor of h multiplied into some quadrature weights, which I will denote by Bm. Okay, so Bm is related to this integral of the Lagrange polynomial over this fixed interval, but you're going to rescale everything. It's like in terms of this factor h, so the h is going to come out, and then the advantage of doing it that is that this Bm will be a constant. Okay, and then you have f y n plus m t n plus m. Okay, so that's the kind of method you get. So the Adams sort of Bashford methods look something like yn plus s is equal to yn plus s minus 1 plus h sum from m equals 0 to s minus 1 bm f evaluated at yn plus m t n plus m. Okay, all right. So this is what is called the S-step Adams-Bashford method. So let's look at a few examples of this. I also sort of say how this BM comes about more specifically. Okay, so BM is 1 over h because if you recall, it's like I factored out this term h here, the integral from Tn plus s minus 1 to Tn plus s of this Lagrange interpolating polynomial. Okay, and you can check that by an appropriate rescaling of the interval, this becomes an integral from 0 to h of Lm applied to Tn plus s minus 1 plus tau d tau. Okay. And the basic idea then is that when you do this, then this object is there's a factor of 1 over h here as well. So when you do this, it's like you'll find that this BM is independent of the time step h. Okay, so you can check that BM is independent of h here. Okay, and also independent of n. Okay. All right. So so perhaps it's easier said. It's like to see how what happens. It's like with a simple example. Okay. So let's look at Adams, Bashford for the s equals to 1 case. All right. So what's happening in the s equals to 1 case, right? That's so you have some time t, all right, and you have t n plus 1, and you have tn. Okay, and what you want again is you want an integral from tn to tn plus 1 of the vector field f. Okay, and the way you do this is with the Adams-Bashford method, the only previous information you have, because s is equal to 1, is just y at time tn. So this is y at n. So and you want to evaluate f on that. Okay. So what that is telling you then is that you have y at n plus 1 is equal to y at n plus, again, the integral of the vector field from the interval time tn to tn plus 1. Okay, so this is plus h times f evaluated at yn tn. And that's because you only are able to construct this polynomial approximation of f from this one value which you have, which is y at tn. So the only possibility you have is something like this. So again, in the s equals to 1 case, it's like all you're really left with is the Euler method. So Adams-Bashford for s equals to 1, right, is the Euler method. So that's perhaps not too exciting. So you can ask, it's like, well, what happens maybe if s is equal to 2? Okay, so let's just see what happens there. Okay, so now you have tn plus 2, tn plus 1, and tn, and again, the time step between each of this is h. You know f at n, you know f at n plus 1, and you want to approximate the integral over Tn to Tn plus 2, right? I want to take the integral from Tn plus 1 to Tn plus 2 of f y tau tau d tau. Okay, so you can check what this is. Okay, so this is approximated by now again some polynomial approximation of the integrand. Okay, so you have 2 points now. It's like, so you can get a linear interpolant, and it's easy to convince yourself that the integral of that linear interpolant is given by h times f at y n plus 1 t n plus 1, right? So you can break up the integral into this rectangular region, which is h times f at n plus 1. So this is what we have, plus this small little triangular region at the top, right, which is 1/2 h times the difference between f at n plus 1 and f at n. So this is just f at y n plus 1 t n plus 1 minus f at y n t n. Okay, so this looks like 3 over 2 h f evaluated at y n plus 1 t n plus 1 minus 1/2 h f evaluated at y n t n. Okay, so so the method you end up getting is this Adams-Bashford two method, right? S equals to 2 method. Okay, is that y at n plus 2 is equal to y at n plus 1 plus 3 over 2 h f at y n plus 1 t n plus 1 minus 1/2 h f at y n t n. Okay, so so that's an example of a sort of two-step Adams-Bashford method. So let me show you a simple example of an Adams-Moulton method. And again, let's consider the s equals to 1 case for the Adams-Moulton method. So so now you have 2 points, Tn plus 1 and Tn, all right? And you know, now you're going to assume you know the vector field values at those 2 times, and you're going to construct a interpolant of the vector field, and you want to integrate over the interval from Tn to Tn plus 1, all right? So you want to take the integral from Tn to Tn plus 1 of f evaluated on y tau tau d tau. So here it should be fairly clear. It's like what you need to do, right? So this is clearly approximable by just the area under the curve. It's like given by this trapezoid. So you can just write down the trapezoidal approximation. So this is going to be f at yn tn plus f evaluated at yn plus 1 tn plus 1. Okay, so so when you put those two things together, that says that yn plus 1 is equal to yn plus h over 2 f evaluated at yn tn plus f evaluated at yn plus 1 tn plus 1. Okay, so this is of course nothing more than the trapezoidal rule. Okay, so the trapezoidal rule is what is called the Adams-Moulton method. In the case s is equal to 1, and if you recall, it's like this is second order accurate. And in general, Adams-Moulton methods are implicit, right, as is the case with the trapezoidal rule, and have order of accuracy sort of s plus 1. Okay, so this Adams-Moulton method is the case for s equal to 1. It has order s plus 1, which is order 2. Okay, and that's perfectly consistent with what we already know about the trapezoidal rule.